All right, welcome back, everybody. This is day one of section 310, linear approximation and differentials. Linear approximations and differentials. So you want to know the gist of today's lesson? Let's take a look here, because it took me a minute to kind of understand what are we doing here. If I've got, we go to a graphing calculator, some weird quadratic function like 3x squared plus 4x minus 10, right? And we see that we know that that's quadratic, right? Right? But what if I zoomed in? Zoom in, please. Does that look quadratic anymore? No. But maybe I just picked a nice, neat point. What if because I zoomed in at the 0. What if I zoom in a part that looks a little curvier? Right? What if I go right in here? Does that look quadratic anymore to you? No, it doesn't look quadratic. That can be done with any type of function. You want to do that same thing with an exponential? Do it with an exponential. You could zoom in at any moment, at any given time along that curve, and see that it's going to be approximated by a linear function. And that's really where this section gets its title. What we can do here is we can take really ridiculously weird functions and say, well, at any given moment, we could find a linear equation that we could say, well, it kind of looks like that linear equation. So let's say that it's going to act like that linear equation. That's what it's called, linear approximation. That's the gist of today's lesson. We've seen that a curve lies very close to its tangent line near the point of tangency. In fact, by zooming in toward a point on the graph of a differentiable function, we notice that the graph looks more and more like its tangent line. It looks more linear, which is what we did. This observation is the basis of a method for finding the approximate values of functions. The idea is that it might be easy to calculate a value of a function, a value f of a of a function, but difficult or maybe even impossible to find or compute the values nearby to that value. So we settle for the easily computed values for the linear function whose graph is the tangent line. Now, this is important to point out here. This is what's called the linear approximation formula. I would write that down. That is actually at the very bottom of your derivative cheat sheet. Okay? That L of x, that capital L of x. Okay? That is what's called the linear approximation formula. The linear approximation formula. Now, to be able to say, I'm going to approximate this weird, wacky function in a linear way, you have to define where you're going to do that. And that's where A comes in. Okay, that's what you're seeing with the notation A. F of A. So we're saying at any given, where did I zoom in? I zoomed in at A. And then I could say, well, if I zoom in at that point, it's going to look linear, and this is the linear equation that's going to be provided by that. Okay, so here's how we create it. You say f of a plus f prime of a times x minus a. Now, that's a weird equation. Where the heck did that thing come from? Well, let me show you. If I take point slope form of a line, y minus y1 is equal to mx minus x1, and I say I want some point a comma f of a, well, I can say y minus f of a is equal to the slope times x minus a, right? But what is the slope at point A? F prime of a. Should have left myself a little bit more room there. F prime of a. Solve that equation for y. Y is equal to, add the f of a over to the other side, f of a plus f prime of a times x minus a. That's your linear approximation formula. Okay, I've got to be honest. We've found the equation of a tangent line like 100 times by now, right? We've done that many, 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 many times. You find the derivative. You figure out where you're going, what point you're doing it at. You plug it in, that's your slope, put it in a point slope, solve for y. We've done that already. Now we're just using it in a different way, in a different mindset, and saying, well, I can approximate that weird, wacky function by a line at any given moment using that same type of process. And we can say, they're calling it L of x, the linear approximation or linearization. Sometimes in the directions it says, like, find the linearization of this function. That same thing. L of x is equal to f of a plus f prime of a times x minus a. And I have to tell you what a is. If I don't tell you what a is, then you don't know where to zoom in at, right? So let's take a look here. Find the linearization of the function f of x is equal to x plus 3 at a equals 1. And we're going to pause there, and I'm going to hide this for right now because we're going to do something with it in a second. So let's just start off by finding the linearization. We're going to linearize. It's a fun word to say, linearization of that function. Now, the linearization of that function, we can compute by saying, well, L of x is equal to, I go back to that formula, f of a plus f prime of a times x minus a. We just have to figure out what all those things are. Okay, so that means I'm going to have L of x is equal to, well, what is f of a? Plug in 1. A is 1, right? Plug in 1 to the original equation. 1 comma 2. 1 plus 3 is 4, square root 2. So this is 2 plus f prime of a. Now, I have to calculate f prime, right? So f of x is going to be, now I'm going to put it as this, like x plus 3 to the 1/2 power, right? Find the derivative. So f prime of x is 1/2 x plus 3 to the negative 1/2. Do I have to use the chain rule? I see something on the inside, so that, like, my gut instinct is to say, ooh, chain rule, something inside, something else. But what is the derivative of the inside? What's the derivative of x plus 3? Just 1. So that'd be like multiplying by 1. You could technically apply the chain rule to anything. So no, I don't need to worry about the chain rule here because the derivative of the inner piece was 1. Mm-hmm. All right, so there's my derivative. Honestly, plug it in now. Who cares, right? I'm not asking you to provide me with the derivative. I'm asking you to provide me with the derivative at 1. So f prime of 1 is 1/2, 1 plus 3 to the negative 1/2 power. I mean, yeah, you could put it as a fraction, but doesn't your calculator do negative exponents? So 0.5 times 4 to the, I'm going to put this in parentheses, negative 0.5 power. 0.25. Sure, you want to make it 1/4? Make it 1/4. 0.25 times x minus 1. And that is the linearization. We know at square root of x plus 3, it's going to act like that. It's going to act like that. Yeah, I guess we can, make it look a little nicer. 2 plus 0.25x minus 0.25. So L of x is equal to 0.25 plus 1.75. So there's the linearization. Let's come back to the rest of this problem now. And we're going to use it to approximate the numbers 3.8, square root of 3.98, and the square root of 4.05. And are these approximations overestimates or underestimates? Overestimates or underestimates. Okay. I'm looking at this here. 1/4 times 0.98. How did I go away from 3? Ah, I see. Okay, what I have to do here is look at this piece inside. Whoa, that's not pen. Look at this piece inside here. 3.98, right? 3.98. What is the x value that gives me 3.98? Looking back here. Kind of switching gears now, solving the rest of this problem. What is the x value that gives me 3.98? What is that x value? X plus 3 is 3.98, right? What x value achieves me getting to 3.98? 0.98. When x is 0.98. Why am I using, well, look, what did I approximate at when a was 1, right? So we're going to calculate that approximation when x is 0.98, and then we're going to do that same thing. Take a look here now. What x value achieves 4.05? 1.05, right? Because I would say that this x plus 3 would be equal to 4.05 and say, well, a 1.05 would achieve that. So those are the x values that we're going to be plugging into the linear approximation. So when I do that, I'm going to say L of 0.98. And then I'm going to calculate L of 1.05, the linear approximation at those values. 0.25 times 0.98 plus 1.75 gives me, enter please, 1.995. And then I take 1.05. We take 0.25 times 1.05 plus 1.75. 2.0125. Now, an interesting piece to this is saying, are those approximations overestimates or underestimates? It might be best to look at a graph to tell me. Let me go to Desmos real quick, and let's, I'm all whacked out on my, can I just go back to like 10 by 10? Okay, I'm just gonna get rid of that tab because I think that this is easier just to get 10 by 10. There we go. Here you go. Okay, so let's go in and graph square root of x plus 3. Squirt x plus 3. Did you guys know that you could type in squirt and it'll go in as a square root, SQRT, and it'll just do that. Isn't that cool? Squirt x plus 3. And then we've got, what was it, 0.25 plus 1.75? Was that it? 0.25 plus 1.75, yeah. 0.25 x plus 1.75. Yeah, 1.75. Okay. Is the linear approximation an overestimate or an underestimate at 1? Let's zoom. Whoa. Let's zoom. And I guess that might be the best. Is my blue line tangentially above the square root or below? Above. So are those values overestimates or underestimates? Those are overestimates. And we see that based on the graph. These are both overestimates. Okay. Sometimes you have to use the graph of them to really kind of tell, okay, is that going to be over? Where is the tangent line? Is it sitting underneath the curve? Is it sitting above the curve? What's happening to it? Okay. What time is it? 9:09? Yeah, we got some more time. Yeah, I'm not going to talk about that. Do I want to do this? Nope, there's a big X through that one. I think this. Nope. Differentials. Skipping to differentials. And this is probably, I'll have to stop and pick up a little bit tomorrow on differentials as well. Understand that we are kind of like at the midway point of calculus, right? We have learned pretty much everything that we can possibly learn about calculating and finding a derivative. Okay, we've only got one more section to do, section 311, and it's really kind of a bizarre section anyway. But we are right now at the midway point of finding everything that we could possibly do about derivatives. You can keep going on this path and keep exploring what are called differential equations, right? In the second semester of calculus, we kind of like switch gears. We talk about more the graphing side, and then we kind of work everything backward. We say like, what's the opposite of a derivative? And that's kind of like the rest of calculus, Calc 1. You can branch off, like in my college career, I had to take 2 classes called differential equations. And what you do in those classes is keep looking at, okay, if I know that I can find the derivative to approximate a certain function, what does that tell you about those new functions that I can create, right? Differential equations. The idea behind linear approximations are sometimes formulated in the terminology notation differentials. If y is equal to f of x, where f is a differentiable function, then the differential dx, right, that's kind of where Leibniz got its notation. Dx is an independent variable, that is, dx can be given the value of any real number. The differential dy is then kind of defined as dy is equivalent to f prime of x dx. Now, where did that come from? Why is dy equivalent to f prime dx? If you really truly say that the derivative, that the differential on y is called dy, and the differential on x is called dx, then how can we say dy is equivalent to f prime x dx? Well, think about point slope form. Y minus y1 is equal to m x minus x1. What is this truly? The differential on y, right? The difference on y. What is this truly? The differential on x, the difference of x. And then we can say, well, what is f prime then? Well, that's the slope. That's the slope. That's f prime of x. And this really kind of introduces the Leibniz notation. If I divide dx over to the other side, it gives me dy over dx is equivalent to f prime of x, right? By that Leibniz notation, we can say that dy dx is really equivalent to f prime of x. So dy is kind of like the independent variable. It depends on the value of x and dx. If dx is given a specific value and x is taken to be some specific number in that domain, then the numerical value of dy can be determined. If I know what if I know what x is and I can evaluate f prime, then I know what the differential on x is. Well, then I can evaluate dy. Sometimes it's used with this delta notation, because doesn't delta mean change in as well, just in like sciencey terms? So we can say dy delta y is equivalent to f prime x delta x, right? So let's take a look here. Compare the values of delta y and dy. Yep. We'll do this problem, then we'll pick the last one up tomorrow. Compare the values of delta y and dy. If y is equivalent to, and f of x is equivalent to x to the third plus x squared minus 2x plus 1. And x changes from, and we got 2 different sets of values, from 2 to 2.05 and from 2 to 2.01. Let's first start by calculating delta y, the change in y. Well, I'm giving you 2 x values here, right? So for part A here, I'm going to find f of 2 and then find f of 2.05. And this is all to find the value of the change in y, delta y. Okay, if I plug in 2 to the third plus 2 squared minus 2 times 2 plus 1. Okay, that gives me 9. I probably could have done that in my head a lot quicker. 9. What about 2.05 though? So 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. 9.717625. 9.717625. Yeah, I'm getting that exact. So what is delta y then? Well, it's just 0.717625. Now, what I'm going to do is I'm going to compare the actual delta y to the differential on y. I'm going to compare the actual delta y and the differential on y. So when I calculate dy, it's f prime x dx. Well, what is dx? What is dx? What is the differential on x? From 2 to 2.05. So I'm going to calculate f prime x times 0.05. Okay, what I need to do is find f prime of x. Well, the nice thing here is, well, that's a polynomial function that's really easy to find. F prime x is 3x squared plus 2x minus 2. What is my x value that I'm going to choose? Let's pick the 2. So 3 times 2 squared plus 2 times 2 minus 2 gives us 14 times 0.05, 0.7. How close was my dy to my delta y? Pretty darn close. We'll pick up tomorrow with what happens if we make that differential on x smaller. Have a good day, everybody.